The Athabasca Basin in northern Saskatchewan is best known as the world's leading source of high-grade uranium and responsible for about 20% of the world's uranium. On the north shore of Lake Athabasca, the Beaver Lodge domain is situated. Historic work in the area dates back to the 1950s. From 1953 to 1982, 16 deposits were brought into production in the Uranium City area, with a total production of over 70 million pounds of uranium oxide, averaging 0.24%. The grades ranged from 0.18 to 0.43%. Most of the uranium deposits in this region are associated with faults, as the faults provide ample fractured ground for hosting uranium mineralization. The main northeast trending faults in the region are the Black Bay and Boom Lake faults, which form the northwest and southeast boundaries of the Black Bay Shear Zone. The Black Bay Shear Zone is a major structural feature which hosts several past-producing mines, such as the past-producing Leonard and Smitty uranium mines, combined to produce 876,000 pounds of uranium oxide, and to the northeast, the Kazor uranium mine produced approximately 1.4 million pounds with unexplored depth potential. The Black Bay Shear Zone is identified as a magnetic low feature. An airborne electromagnetic, more commonly known as an EM survey, identified a conductor corridor within the Black Bay Shear Zone. EM conductors may reflect structurally reactivated graphitic basement rocks. Electromagnetic conductors mark graphite in the basement rocks, and graphite is key for finding uranium in the Athabasca Basin. Many large uranium deposits are associated with graphite-rich faults, which are thought to have acted as near-ideal traps for triggering deposition of unusually large and high-grade ore zones. And it is precisely in this area that Belmont's Crackingstone Uranium property is situated. The Crackingstone property is situated within 6 kilometers of 4 past-producing uranium mines. The property covers 5 kilometers of the Black Bay Shear Zone. A 2007 airborne magnetic survey over the Crackingstone property provided higher-resolution magnetic imagery showing a strong magnetic low feature over most of the southeast area of the property, which is interpreted to be the Black Bay Shear Zone. On the property, and on strike with the Black Bay structural corridor, are the northeasterly Chance Lake and Boom Lake faults. A magnetic first vertical derivative map highlights the magnetic low fault trends on the property. These faults appear to have been reactivated several times to provide ample fractured ground for hosting the uranium mineralization. There appears an area to the east that a structural feature extends westward onto the Crackingstone property. This has been labeled as the Crackingstone Fault. This fault, and other parallel subfaults north and south of the Crackingstone Fault, appears to intersect other northeast trending faults, such as the Boom Lake Fault and Chance Lake Fault. The intersection points of these northeast faults and east-northeast Crackingstone faults appear to be a selected area for the concentration of uranium mineralization as illustrated at the Cinch uranium mine. A fourth fault, named the Nero Lake Fault, extends from the Black Bay Fault in the east, westerly across the southern portion of the property. A 2007 ground EM survey identified 2 prospective conductive low magnetic signature corridors on the property, which run parallel to the major northeast trending faults. The 2 distinct corridors have a total strike length of over 5 kilometers. Since the early 1950s, numerous uranium occurrences throughout the property have been discovered, mapped, and assayed. In 1958, Mr. E. Cull, who drove a short adit, which is now referred to the number 7 adit, from the base of a trench, which previously returned 15.6% uranium oxide over 1.4 feet. He shipped 11 tons of broken rock to the Laredo mill, which graded 2.3% uranium oxide. In 1959, at the Beck 58 showing, channel sampling returned 1.7 feet of 0.36% uranium oxide and 1.6 feet of 0.36% uranium oxide. Mr. C. Hanilika high-graded approximately 46 tons, which graded 0.5% uranium oxide. Also in 1959, uranium stain was visible at a few places near the Beck 91 showing. A channel sample assayed 2 feet at 0.95% uranium oxide, and a bulk sample from the same locality assayed 3.86% uranium oxide. The center portion of the showing was high-graded by M. Filgas in 1959. Hand-sorted 6.5 tons, grading 0.5% uranium oxide. A grab sample containing considerable yellow stain, possibly fine disseminated pitch blend, from the Beck 93 showing, assayed 12.53% uranium oxide. At the Beck 231 showing channel sampling assayed 1.32% uranium oxide over 2.1 feet, 2.13% over 2.3 feet, and 1.46% over 1.6 feet. At the Beck 102 showing, a grab sample assayed 5.2% uranium oxide. In addition to these high uranium assays, strong radioactivity was measured on surface in numerous showings across the property. In uranium exploration, a handheld device called a scintillometer is used to test the radioactivity of rocks. CPS, or counts per second, is a measurement used to determine how radioactive something is. The higher the better. Greater than 300 CPS on the handheld scintillometer would be considered anomalous. Greater than 10,000 CPS would be considered high-grade, and greater than 65,000 CPS would be considered as off-scale. In the southern portion of the Crackingstone property, readings ranged from 3,000 CPS to over 65,000 CPS. Worth noting is that these readings were coincident with EM conductors. In the north, readings ranged from 6,000 CPS to a high of 13,000 CPS. In October of 2007, Belmont Resources contracted MPX Geophysics to fly a radiometric survey over its Crackingstone property. A radiometric survey, or as it's also referred to as gamma-ray spectrometry, is a surveying technique that allows the calculation of the heat produced during radioactive decay of uranium, thorium, and potassium within the Earth's surface. Many natural elements have radioactive isotopes, but only uranium, thorium, and potassium decay series produce sufficient energy and intensity to be measured by gamma-ray spectrometry. The results of the uranium survey show 2 large uranium anomalies in the northeast and southeast areas of the property. When we combine the previous exploration data to these results, we see that the northeastern uranium anomaly is coincident with the 2 northeasterly trending faults, EM conductors and uranium occurrences at surface. The easterly Crackingstone fault appears to create a break between the 2 anomalies. The southeast uranium anomaly tends to trend more easterly and appears to be influenced by the Nero Lake Fault. First vertical derivative of uranium data is an algorithm which enhances the shallow sources of uranium by suppressing the effect of the deeper ones. This helps to highlight potential near-surface uranium mineralization. On the first vertical derivative, Crackingstone map, virtually all uranium occurrences mapped at surface are associated with the uranium first vertical derivative anomalies. This strong correlation confirms that the first vertical derivative uranium map is an effective map for targeting other yet unexplored areas of the property for uranium. In 2007, Belmont focused its exploration on the intersecting east-west and northeast structure along the Crackingstone Fault, Boom Lake Fault system, especially north of the Crackingstone Fault along the Boom Lake Fault. Samples taken from the number 7 adit returned 6.5, 0.78, 0.40, and 0.28% uranium oxide. A detailed gamma-ray survey carried out in this area identified a large area of high radioactive anomalies coincident with the Boom Lake and Crackingstone fault systems. In March of 2008, Belmont carried out a 20-hole, 3,000-meter diamond drilling program covering an 1,800-meter strike length along the Boom Lake Fault. All of the drill core was mineralized with uranium, along with pegmatites and hematites. Holes C14 and C8 both yielded high assays, with C14 having the highest CPS reading and assay sample of all the holes. Assays in C14 ranged as high as 2.08% uranium oxide over 0.5 meters, and this is part of an interval of 0.9 meters, averaging 1.18% uranium oxide. In addition to the uranium mineralization, drilling also intercepted an apparent 1.8-kilometer pegmatite dike. Pegmatite is often associated with uranium mineralization in the Athabasca Basin. Of even more importance was the extensive amount of hematite intercepted across the entire 1.8-kilometer zone. Hematite is an alteration type often associated with uranium, and the occurrence of hematite in alteration zones is an indication of uranium precipitation during the hydrothermal event. The results of the 2008 drilling were very positive, with the interception of uranium mineralization along with pegmatites and hematite alteration along the Boom Lake and Crackingstone structural fault zones, confirming the methodology of exploring the intersection point of the structural features and the discovery of new zones of mineralization not previously known. In preparation for a 2024 exploration program, Belmont has compiled and modeled over 75 years of exploration survey data from the Crackingstone area. After reviewing the newly created database, 18 high-quality targets have been chosen based on their proximity to a major fault, presence of an EM conductor, uranium first vertical derivative anomaly, and uranium surface occurrence. Out of these 18 areas, 4 have been selected for drilling in 2024. These 4 drilled targets are situated on the Boom Lake conductive corridor, and based on an extensive review of the exploration database, and along with a review of the positive results of the 2008 drilling, are considered to have a high probability of successfully extending the uranium mineralized zone encountered in the 2008 drilling. Belmont is now planning to return to its Crackingstone uranium property for the first time since its successful 2008 drilling program. Ground truthing of the 18 targets is expected to commence in Q2 of this year depending on ground conditions, and drilling is planned for Q3 or Q4, depending upon the timing of drill permitting approval.